Today we will talk about neural networks. So let's recap what I've done so far. So we have seen linear regression, and we have also seen logistic regression to do classification. Now today we will see neural networks, and we will use them to make regression and classification. And then we will see how in other lessons how we can use it for dimensionality reduction. But for today, let's focus on just this. First, I will describe what is a neural network, what is its mathematical structure. Then I will describe how we can train them, and in particular the technique called backpropagation. And we will discuss some design choices related to the architecture and other hyperparameters of the neural networks. And as usual, at the end, I will show you the code to use neural networks in practice in Python. So, neural networks were introduced in 1943 by this article here, a logical calculus of the ideas immanent in nervous activities. This is one of the nicest articles I've read, so I invite you to read if you're interested, because it is simple and it is evident that there are some brilliant and very innovative ideas inside this paper. Actually, this is the result of a collaboration between two scientists from two different disciplines. Walter Pitts, who was a logician, and Warren McCulloch, who was a neurophysiologist. So this is a demonstration of how smart ideas sometimes can come from very different people working together. So we can say that an artificial neural network imitates in some way the neural networks that are present in animals or humans. A neural network, a biological neural network, is composed by several neurons. Each neuron has different axons in which an electrical signal is propagated. So a neuron collects these signals in inputs and activates or not, meaning that it can generate, based on the input received, another electrical signal that can be propagated to other neurons. This is how the information coming from our senses, our eyes, our ears, is processed and transmitted into the brain and processed into the brain to extract some knowledge or take some action. And these scientists actually took inspiration from this, and they claimed we can actually imitate the way the brain works, and we will see how it can be done. And just as a side information, actually Walter Pitts is a clear demonstration of a genius. So when he was just 12 years old, instead of playing with his other friends, he was already reading books of logics. And actually he was also criticizing books from very well-known logicians at those times, like Bertrand Russell. And actually he was also invited, so Russell, that was like a sort of star in science, he invited this kid to work with him. And actually Walter Pitts refused, and then he continued his scientific career independently and with very big results. Observe that this paper is from 1943, so neural networks are not at all something new, but they were acclaimed at the beginning, then they were sort of abandoned for a while, and now in these decades they are coming back as the trendiest method in machine learning because of the improvements that have been done in these years, and also because of the availability of high computation power. So now we will see that neural networks require a lot of computation to be trained, and now we are able to make this computation in a relatively easy way, thanks to GPUs and other parallel architectures, parallel computer architectures. So the simplest neural network is called multi-layer perceptron. So let's see how it is done. So first we have the input layer, where we just connect our samples, let's say. So here, this vector here is just one sample, and this is the feature 1, feature 2, feature 3 of the sample, and we add, as usual, a 1. Okay, then we have neurons that are structures like this. Each neuron takes as input some parameters, also called weights. So for example, the parameter of the first neuron in this first layer are these, etc. So then at the output of the neuron, it is another number is generated, and so at the output of each neuron we will see a number, and this vector here is called output of layer of the first layer, and this output is again propagated to this other layer, composed in this case by these other two neurons, and at the end we will have an output. So let's see more closely what happens into one neuron and what are the mathematical operations that we have there. So suppose these x1, x2, etc. are the output of a previous layer, or they can also be simply the input vector, the feature vector. It doesn't matter. So, and let's take just one neuron. First, we indicate with this vector x of L minus 1, this vector composed by x1, x2, x3 plus a 1 that we always add at the beginning. These weights, okay, form a vector of weights of neuron Q in layer L. Then we compute the weighted input, this number here, that is the scalar product between the vector of weights and the vector of x. This result is called weighted input, and it is indicated by this A. And we give this result as input to an activation function that I indicate with this sigma. And this activation function is also called sometimes nonlinearity. Okay, and we will see what is the form that it can have. And the output of the activation function, that is here, is then propagated to the following layer. So you have to imagine that there are also other neurons in which the same operation occur, and so you will have the output of the other neurons Q prime, output of the other neurons Q second, etc., etc. So this output vector here of x will constitute the input vector of the next layer. So if you have another neuron here, all these outputs will be going in input to this other neuron, and here we will have other weights. Okay. So the beauty of a neural network is that the fundamental computation is always the same. The complexity that they can represent is just given by the complex combination of these neurons. So I've talked about this activation function sigma. This can be different. This can have different forms. It can be a sigmoid, hyperbolic tangent, etc. And you have to choose one of them. Again, how can you choose? Just by trial and error. So now you can combine this fundamental unit that is the neuron in different ways. So you can just have one neuron, and what you obtain is a logistic regression that we've seen in the last lesson. Or you can have more neurons, but just one layer. Or you can have two layers. Or you can have many layers. So if you have few layers, we talk about a shallow neural network. If you have many layers, it can be 100, whatever, you talk about deep neural networks. And actually, the input, so the first layer is usually called input layer, and this is composed by the features themselves. The result is called output layer, and actually all these other layers are called hidden layers. So we will now see how to use neural networks for predictions or inferences, and then we will see how to train them. You will see that during prediction the information goes from left to right, and we talk about forward propagation, while during training the information goes from right to left, and we talk about back propagation. But you will understand these terms later. So suppose for the moment that someone already trained your neural network and it gave you all the weights with a certain value. So you have now just to use the neural network for regression. For instance, you can imagine that the input features are, as we did in the last lessons, are information about internet connections. For example, number of bytes exchanged between the client and the server, number of packets, etc. And in the output, you want to have the resolution that the video resolution that the user is watching. So you give each sample and you have a resolution. Let's see how the feature vector at the beginning with the internet information is then transformed into the final answer. So first, let me go slower. So first you compute the weighted input, that in this case is A of layer 0 of the first neuron, which is the scalar product between the weight entering neuron 1 in layer 0, which is the vector of these weights that are entering neuron 1, okay, multiplied by the input vector, which is this other vector here. So, and then you apply the activation function, a sigmoid or whatever, and what you obtain is this output here. You do the same for all the neurons. So at the end, what you will have is you have an entire output vector of this first layer. This vector here will be the input of the next layer, in which the same computation will happen. And the same computation will happen also in the other layers and in the final layers as well. And this is where you have your final answer, y hat. Okay, so at the end you always have your feature vector at the input and an answer in the output, and actually all the set of features, all the set of parameters determines the shape of your approximation function. So this structure here is very flexible, because by combining all this computation, you can show with this theorem of universal approximation of neural networks that you can approximate any continuous function. So if someone gives you any function f of x that is continuous, you can always find a parameter vector theta such that your approximation function is close enough to this continuous function. So this is true provided that you have enough neurons. Okay, so neural networks are powerful because they are flexible, maximally flexible. They can imitate any continuous function relating input and output. So what I've just explained is related to regression. So this y here is a number. We can use the neural network also to do classifications. For instance, the input of neural networks could be pictures, and for instance, each numerical value corresponding to a pixel could be one of the features. And at the end, the answer could be something like 0 or 1. 0 if the picture represents a dog, 1 if the picture represents a cat. Or in a similar setting, in a communication network, we may want to collect measures regarding our infrastructure, like delays, error rates, etc. And then at the end, having an answer categorizing what is happening in your network. If there is a low severity problem, or a mid severity problem, or a high severity problem. This was the kind of task that Telestra, that is a communication network in Australia, demanded in a competition, in a data science competition. So they wanted people to construct machine learning models, and for example neural networks, in which you give in input the features of network measurements in a certain time window, and as output you want to know the severity of the event that corresponds to that observation window. So in this case you have 3 classes and you want to distinguish between them. So when you use a neural network for classification, actually the operations are the same as we saw for regression. So the computation is exactly the same. I will not repeat it. What changes is just the output layer, which is actually identical to logistic regression that we've seen before. In fact, you first compute the score of each class. So the score of class number 1, for instance, is the scalar product of this vector of parameters entering neuron 1, which is the parameters of layer 1 entering neuron 1, multiplied by the input vector of this layer 1, which is this vector here, this vector here. Okay. So this is the score. It's a scalar number. Then we perform softmax, which means that we do the exponential of the score of class number 1, and we normalize by the sum of the exponential of all the other all the scores. And we do the same for class number 1, class number 2, and class number 3. At the end, we have something that is between 0 and 1, and it sums up to 1. So it can be interpreted as a probability. So suppose we have a certain event with certain features corresponding to network measurements, and in the output we have 0.7 probability of that event being class 1, 0.1 of being class 2, 0.2 of being class 3. The highest probability is for class number 1, so we will classify that event as class number 1. So observe that for regression or for classification, neural networks have exactly the same structure. What changes is just the last layer. So this is also a nice feature of neural networks. Mathematics is the same, you just change the last layer and you can do very different tasks. So far we have assumed that someone gave us the neural network already trained with all the parameter vector theta already established. Now we will see how we can train the neural network ourselves, which means how we can find the optimal parameter which minimizes the loss function. So we first need to establish a loss function, okay? So if we are performing regression, we usually use mean square error. So this is the loss function of sample I, just one sample, okay? And this is the mean square error, the difference between the true value and the predicted value squared. If we want to know the total loss, we have just to sum over all the samples. When we have classification, instead, the loss function is the cross entropy. What is cross entropy? We have defined it in last lesson, but let me explain it again. So suppose so this ki is the true class of sample I. Suppose, for example, that for a certain sample x, the true class is class number 2. When we compute the loss of the prediction on that sample, we ignore all the other predicted probabilities. We just focus on the predicted probability of class 2. And the loss is minus logarithm of p hat 2 I. So because ki is equal to 2. Now let's see an example. So suppose that for this sample here, the predicted probability was very low, 0.001 for class 2, and for class 1 it was very high, 0.999, while for class 3 it was actually 0. So in this case, our neural network would be wrong because it would predict class number 1. So let's see what is the loss function in this case. Okay, we just need to compute minus logarithm of 0.001. So 0.001 is close to 0. So the logarithm of this is close to minus infinite. And so the loss is minus infinite, which means plus infinite. So you see that, and of course this is a huge loss. So you see that whenever your neural network predicts the wrong probability at the exit, okay, a low probability for the true class, then your loss explodes. So when we perform this optimization problem, we are trying to find the parameters which prevents this situation to happen, which prevents to have high probability for the wrong class. We want to predict high probability for the true class. Otherwise, the loss function explodes. So, how can we solve this optimization problem? Well, we use again gradient descent as we did with logistic regression. So gradient descent is an iterative algorithm. So first we randomly generate an initialization vector, okay, using specific techniques. So it's not actually completely randomly, but there are specific techniques to do it properly. We will not see them anyways. Then at each iteration we will first compute the gradient of the loss function, and then we will update the parameter. Okay, observe that the gradient is a very big vector because it's the derivative of j of the loss function with respect to any single weight. So we have the weight of layer 1 exiting from or layer 0 exiting from 0 going to 1, then the derivative of always layer 0 exiting from 0 from 1 and going to 1, etc., etc. So if we come back to this, we have to compute the derivative with respect to this parameter, to this parameter, to this, to this, to this, to this, and to every and all the parameters. So the gradient is a big vector, is as big as the dimension of the parameter. And then we apply the gradient descent equation as we did for logistic regression. But there's a difference. In logistic regression, the loss function is guaranteed to be convex. It means that there is only one minimum. And so when you apply gradient descent, you're sure you will go to this point where the gradient is 0, and you will not move away from it. So you will for sure converge to the optimal parameter, which minimizes the loss. In neural network instead, the loss function is very complicated, okay, because it is the result of a lot of layers, a lot of neurons. So the loss function, if we represent it in just 2 dimensions, so where this is just one parameter theta 1 and this is just one parameter theta 2, it looks something like this. Of course, in a neural network we have not just 2 parameters, we have thousands of parameters, but this is just a visual representation. So the loss function in a neural network is not guaranteed to be convex, which means that there can be different local minima in which the gradient is 0. And so your gradient descent algorithm may actually converge to one of these local minima. So we say that it is trapped in a local minimum. And so this local minimum can be different from the global minimum. So when you have the result of the gradient descent in a neural network, you can't be sure that you are actually minimizing your loss function, because there can be another minimum that is better somewhere else, and you're trapped in a bad minimum. For instance, here this is a bad minimum because this other minimum here is deeper, so the loss function is smaller there. So if we are trapped around this point, our loss will remain unfortunately high. This is a limit of neural networks and we have to cope with it. Now, we have seen that to perform gradient descent in order to find the optimal parameters, we have to compute the gradient. How do we compute the gradient? Well, the gradient is, as I told you, a set of derivatives with respect to any parameters. To compute these derivatives, we use an algorithm called backpropagation, which is nothing else than applying derivatives over and over again. So the computation is quite simple but also cumbersome. I will skip the details and I will go directly into the meaning of it. So we are training our neural network. So we have our training set and we take our training samples one by one. Let's take the sample x1, for instance. We first do forward propagation to compute our prediction on it, and so we first feed the first layer of neurons with these inputs. We obtain the output that we feed into the second layer, and we continue until we arrive at the end. At the end, we have our prediction y hat. We see the difference with respect to the true value of the label, and we call this difference residual, as usual. Well, with the residual, we can immediately compute the derivative with respect to the parameters in the last layer. So if we take any generic parameter in the last layer, like the weight of this connection here, let's call it theta q, well, it is just the multiplication of the residual by the corresponding outputs on that connection. Okay, so computing derivatives in the last layer, it's easy. Now we have also to compute the derivatives on all the other layers, which is a bit more complicated, but nothing impossible. So before we continue, let's define a quantity delta that we call error. I will not explain why, but observe that the error on a certain layer L-1 depends on the error on the following layers, on the following layer L. Why do we need such an error delta? Because it is useful to compute the derivative on layer L-1. So observe here that the derivative of the loss function with respect to a parameter in layer L-1 is just the multiplication of this error in L-1 by the corresponding outputs of a neuron of the neuron in that layer. So the derivative is just computed directly based on the error, and the error on a certain layer depends on the error on the following layer. So this is the reason why this algorithm is called backpropagation, because we are taking an error observed in a certain layer and we propagate it back to the previous layer. So by doing this, we are sort of learning from the error. So we first do forward propagation to have a prediction. Then we observe the error at the end and we use it to update the error in an intermediary layer. We use the error here to compute the error in the previous layer, so on and so forth, until we cover all the layers and we arrived in the first layer. So like this, by playing with these errors, we are able to compute any derivatives or with respect to any parameter. So at the end, if we have all the derivatives, we have the complete gradient. And we repeat the same process for all the samples, x1, x2, xi in general. By just averaging across all the samples, we obtain the global gradient of the loss function. And we can apply it to the gradient descent. So let's recap what we have done. We have used backpropagation just to compute the derivatives with respect to all the parameters. These derivatives form our gradient that then we use to update our parameter vector in the algorithm called gradient descent. As we did for logistic regression, we can apply gradient descent in different fashions. Either full gradient descent, in which first we traverse the entire training datasets and we compute the gradient of the total loss function, and we use it to update the parameter vector. This is the simplest way of applying gradient descent, but if your training set is too big, this takes a long time. So an alternative is to use stochastic gradient descent, in which you take every time one random sample, you compute the loss function on this random function, and you do immediately backpropagation. And you compute the derivative of this loss function with respect to all the parameters, and you immediately update your parameter vector by using this equation. An approach that is in the middle between these two is batch gradient descent, in which you take a batch of samples, like 32 or 64, and you compute the gradient of the loss function just based on this subset, and you update your parameter vector. As in the logistic regression, an epoch is a traversal of the entire dataset. So if we do full gradient descent, we update the parameter vector once per each epoch. If we do instead stochastic gradient descent, we update the parameters many times for each epoch. So in our computers, when we do these operations of gradient descent and backpropagation, our parameters are stored in variables inside memory cells. But actually, in the beginning, the first experiments with neural networks were done with these kind of monsters here, where each weight was a potentiometer, and updating the parameter vector meant to adjust these potentiometers with motors. Okay, so nowadays life is way easier than before. Now, we have seen that neural networks are composed by very simple fundamental elements that are these neurons, which take a scalar product as inputs. They apply an activation function, and that's all. But by combining them, we can do a lot of complex tasks. So there are many ways of combining these elements, and so the design of a neural network forces you to choose many aspects, and so to have the right neural network that performs well on your dataset is very difficult. Also, the different architectures correspond to different aims you have. For instance, if you have an architecture like this one on the left, you start with many features, and as you go on with the layers, you reduce the number of neurons. In other words, you are compressing the information, you are forcing it to be stored in less elements than the beginning. So you are doing dimensionality reduction, in other words. You can also do the opposite. You start with a certain feature vector, and then in the hidden layers you have more neurons than the dimension of the feature vector. In this way, you are instead augmenting the representation of your data. So you can play with these architectures depending on what you want to do. Then you have to pay attention, because the more common problem of neural networks is that they overfit. We have seen that neural networks can approximate any continuous function. This is good, but this can also be very bad, because they are so flexible that they can adapt too much to your dataset. And so they can be unable to generalize. So how can we avoid this? The first thing is to try to keep your neural network parsimonious. So don't try to put as many neurons as possible, but sometimes it's better to reduce the size of your neural network. This is one way of thinking it, but other people may think the opposite. Just throw many neurons and it will work right away. So this is still an open debate. Another way to avoid overfitting is regularization. That is what we have seen already in the previous lessons, which is just by modifying the loss function, adding to the error term also a regularization term, which keeps the weights of neural network small enough. Another way is early stopping. So it works like this. So in this picture, I'm representing the loss function on the training dataset and on the test dataset. So the blue curve is called training loss, and the red curve is called validation or test loss. So each point corresponds to an epoch. So as we go on with the epochs, of course, by gradient descent, you will adapt always better to the training set. And so your training error will decrease for sure. And at the beginning, your validation error will decrease as well. But at a certain point, you start to overfit. So your network loses the capability of generalizing. And you see that your test loss starts to increase instead of decreasing. In this case, the simplest thing to do is just to stop. So you will see that in the Python libraries we will use, there is an easy way to tell the neural network, well, if you observe that at a certain point, if you go on with the epochs, your validation loss is not decreasing, but it's on the contrary increasing, then stop and give me the parameters that guaranteed the lower loss function. Another thing you should pay attention to is to scale your dataset before giving it to a neural network. This is because some activation functions that may be used inside the neural network, like a sigmoid, are sensible to the range of the input values. For instance, if you take a sigmoid like this, if you give as inputs -1 million, or if you give values that are in the range between -1 million and 1 million, you will actually have as a result either 0 or 1. So you are losing the smoothness of the sigmoid. You are not exploiting it. So it is always advisable to scale your dataset. Then there are a lot of other design choices. So we have seen that when you apply gradient descent, you have this parameter eta called learning rate. This has to be set properly, because if it is too large, you update every time your parameter by you change your parameter vector too much. So you may jump a lot and you may never converge to a minimum. And worse, if this is way too large, you will also see that you will jump away from the minimum. Okay? On the other hand, if the learning rate is too small, you will go toward the minimum, okay, but you will go too slowly. So the best is to find the right learning rate. Okay, here you see some examples of losses with respect to the epochs with different learning rates. So the low learning rate decreases the loss, but too slowly. The very high learning rate keeps you away from the minimum. while a good learning rate decreases quite fast and then it keeps decreasing the error, the loss. But how can you choose the right learning rate? Well, the best thing to do is not to keep this learning rate fixed, but to do some scheduling. So to change it as epochs go on. So you start with high learning rates and then you make them smaller and smaller when you go on with the epochs. Also, we have just seen for the moment classic gradient descent. That is this equation here. Actually, there are other optimizers that perform better. These are just, let's say, enhanced version of gradient descent. And actually, the most used one is Adam optimizer. And in this website, you have a nice comparison of different of different optimizers, and you see how the parameter vectors converge toward the minimum. You see that stochastic gradient descent is very slow compared to the others. Okay. So you will likely use Adam instead. Another thing you should use is the batch size, and this is still an open question. Should I use 32 or 64, etc. Then you should also choose the activation function. So for the last layer, you don't have to choose anything because the choice is determined. If you want to do regression, use a linear activation function. I mean, that does nothing essentially. If you want to do classification, you use softmax. The choice is in the intermediate neurons, where you can choose sigmoid, ReLU, etc. Actually, in previous decades, sigmoid was the preferred one because it was thought to be what happens inside our brains. But actually, sigmoid is not the best choice. So it has been shown, and you can see the reference here, that it's better not to use sigmoid but other functions like ReLU or exponential LU, etc. Then, so far we have just focused on this simple structure of neural network that is called multi-layer perceptron, in which you have your inputs that goes to a certain hidden layer that produces an output which goes as input into another hidden layer and again into the next hidden layer, and so on and so forth. But you may have more complex architecture in which the output of a certain layer can skip some layers, like here, and can go directly to some other layer. But we will not have the time to cover this, so it's just to mention it to you. Then you have specific architectures of neural networks or deep neural networks for different tasks. For instance, convolutional neural networks are used for image processing, or recurrent neural networks for time series analysis. We will see in this course autoencoders that are useful for anomaly detection. You also have generative adversarial networks that are used to produce new information, like produce music, produce new pictures, etc. But we will not have the time to cover them. So in the other slides, I put the explanation of convolutional neural networks, but we will skip it for this year. So let's go directly to the code to implement neural network in Python. To run neural networks in Python, we will use Keras and TensorFlow. Actually, TensorFlow is the library that does the actual computations for training and predicting with neural networks, while Keras is just an abstraction, is an interface which hides the complexity of TensorFlow. You have other alternatives out there, For instance, while Keras and TensorFlow are proposed by Google, also Facebook has its own library called PyTorch. So, but let's use Keras for this moment. So, when you train a neural network, if you have some GPUs or TPUs, training will be much faster, because intuitively you can understand that training can be easily parallelized. So GPUs and TPUs are architectures that are much more parallel than classic CPUs. And in Google Cloud, you can exploit the TPUs and the GPUs there by just clicking on runtime, change runtime type, and you can select either a GPU or a TPU. Okay, now let's run the code. Actually, at first, as usual, we import the libraries. You can check what are the libraries yourself. Then this time we will mount a Google Drive. Why it is important? Because training a neural network takes usually a long time, hours at least, or sometimes also days. And so imagine if something happens in the middle of your training, so your machine crashes or there is some other error. So you will lose all the computation you have done so far. In addition, you have to consider that Google Cloud is kind to you because it lets you run your code on their premises for free, but they will not let you run forever. After a while, they will disconnect you. And this time is variable. You will not be able to predict it. So it would be a pity if every time this happens, you have to train your network from the beginning. So it is safer instead to save the neural networks that you will be training in your Google Drive. To do so, you have to connect your Google Drive. This is the code to do it. And actually, when you run it, you have to click on a link. You have to connect with your Google account. You have to allow everything, and then you have to copy this passcode. Copy and paste it here. Okay. By doing this, you're telling you're telling Google that you want to write files on your Google Drive. Actually, here I'm using this folder in my Google Drive, TSP, teaching, data science, etc. That actually correspond to a folder that I have in my Google account. So you will replace this folder with your own folder. In this notebook, we will use a dataset used in a work published in Computer Communications, which is a journal of Elsevier, in 2019. The goal of this work was to be able to estimate the available bandwidth between a pair of endpoints. So when two endpoints communicate over a link or over a network topology, for example, over the internet, they will the information that they will exchange will traverse a sequence of links. But these links will also be used by other communications. So there will be some cross traffic that consumes the capacity of the links. So not all the entire capacity of the network is available for the pair of endpoints, because a part of it will be consumed for the cross traffic. So who can tell to the endpoints how much is the bandwidth available to them? Well, nobody, because they just have they don't have the complete view of the entire network. So they don't know who else is there sharing the same links. So the goal of this work is to show that it's possible for these endpoints to estimate the available bandwidth just by using measurements collected in the two hosts. Why it is important? Because if, for instance, the one endpoint is a video server and the other endpoint is a video client, if the available capacity, the available bandwidth to them is known, the client can better choose the video resolution that it should download. For instance, if there is a lot of available bandwidth, the client can download high resolution videos. Otherwise, it should go back to low resolution videos. Actually, taking this decision seems trivial nowadays, but actually is still an open research problem. How to choose the proper video resolution when we consume video streaming. So estimating the bandwidth is still an actual problem and it's still interesting. So how can we estimate it? Well, the idea is simple. So if on the one hand we send a sequence of packets, in the other hand we will see the same sequence of packets distorted, because in the middle between one packet and another, in some of the traverse links, there will be other cross traffic flowing. So the packets in the output will be delayed. So if we measure the data rate on the one side in inputs, R in, we will measure a data rate on the other side, R output, usually smaller. So by just measuring these two values, we want to infer this lambda here. That is the available bandwidth between these two endpoints. Here I'm representing just one link, but actually this link could also be a complex topology or the internet. So let's first see how the authors created the datasets. So they set up a testbed where they had different machines. First, the pair of endpoints for which they want to measure the available bandwidth, that is a video server and a video receiver. So the traffic they exchange crosses different links, and so different routers. And these links are also used by other machines that produce cross traffic. So in each experiment, they just send some packets from video server to video receiver, and they measured these R in and R out. Okay, and they repeated the experiment first with cross traffic equal to 25 megabit per second. Then they repeated the same experiment with cross traffic equal to 50 megabit per second, and so on and so forth. So at the end, they had a data set that looks like this. So here I'm downloading the data set, I'm unzipping the file. So their dataset is first divided into parts, a testing dataset and a training dataset. If we look inside the training dataset, here we have all the experiments where the total capacity was set to 100, or here 50, etc. If we look into this experiment with total capacity 100, we see that in this folder we have all the experiments where the cross traffic was 25 megabit per second. Here the cross traffic was 50 megabit per second, etc. So since the traces are collected in a controlled experiment, they knew in advance what was the what was the cross traffic, and so what was the available bandwidth in any experiment. Actually, how did they measure precisely this traffic? Well, they used a card like this called data acquisition and generation, DAG, which is used by network operators to measure traffic and to timestamp packets in a very precise way. So if you look at a single experiment, we see that actually at a single configuration, here we're looking at total capacity 100 megabit per second and cross traffic 75 megabit per second, we see that the authors repeated many experiments, more 100, I think. And if we look into the single experiment, this is what we have. So we have this information. This is not actually the header of the file. This is just the information that the available bandwidth in this experiment was 25 and the total capacity was 100. And then we have these values. The second column is just a timestamp that we will ignore. The first column is instead what we will use, and is the ratio between R in and R out. So ratio between data rate at input and data rate at output. Okay, so it's the ratio between this value and this other value. Here I'm just renaming the columns. So how can we transform this data set in a set of samples that we can use to train our neural network? So we have to do some feature engineering. So one single experiment will be one sample, okay? And this sample will be just represented by the histogram of this value of ratio, R in divided by R out. So for instance, in this case, the sample is a vector with the following numbers: 2.4, 1.2, 0.6, etc. So this vector is our sample we will use, and the label of this sample is known, is the actual available bandwidth that we know because we set an experiment setting this value. So here is the function just to download all the files and to load in one single data frame. So I'm just establishing that I want all my histograms with just 8 bins. Like this, I'm sure that all the samples will have the same number of features. So one feature corresponds to one bin of the histogram. Okay. So this is actually doing what I told you. First, so let's see if I... Okay. First let's check what how many samples we have with available capacity 12.5 and 25, 37.5, etc. We see that our dataset is unbalanced because there are many samples with available capacity 25 and less samples with available capacity 75. So we use synthetic minority oversampling technique that we explained in last lesson to avoid any problems related to that. Then we scale the dataset as we did last time, and we do one-hot encoding for the label. So now the label is a numerical value, so if we want we could also run a regression, but since this numerical value can just take a discrete number of values, 25, 75, 50, etc., we choose this time to instead run a classification. And so we transform this label by using one-hot encoding. So instead of having just one column, we have one column per each possible value. And each sample will have a 1 in the corresponding column. Now, let's build a neural network model. So first we set the seeds so that every time we repeat this notebook, we will always have the same values. So this is to allow repeatability. We fix the learning rate and then we build the model. Observe that it is I'm here defining a function that builds a model. This is convenient because like this you avoid every time to write the same code. Okay, So I suggest you to do the same. So let's see what is this neural network. Actually, we are adding 1, 2, 3, 4, 5, 6 layers. The first layer, of course, has the same dimension as the input, that is 8, that is the number of bins. And then we have the first layer of 200 neurons, then second layer 50, 30, etc. And observe that I chose as activation function a ReLU, and in the last layer I choose, of course, the softmax, because we are dealing with the classification. And the number of neurons as output is equal to the number of classes I want to distinguish. Then I have to compile the model, where I also need to specify the other hyperparameters. What is the loss I want to consider? What is the optimizer with the learning rate? And what is the matrix that I want to plot? We will see that plotting the metric is useful when you train a neural network. After you build the model, you can print a summary like this that tells you how many layers you have and how many neurons per layers. And you can also have a graphical representation that I think is not very useful anyways. Now, as we did for all the other models we have seen so far, we have just to train on the training sets and then just test. When we train, we also say that we also specify a validation split. It means that our neural network will just take the training set, will divide it in two parts, an actual training set and another part that will be the validation set. So the neural network will just use this subpart, the training subpart, and will just to train, and the remaining part will just use for evaluation purposes. So let me write here the representation. So here we are giving the training set, okay, the entire training set, X train and Y train, to the neural network, okay? Because the test set is aside in another file that we didn't download yet. So far we are not seeing this. Actually, we are telling the neural network to divide the training set in other two sets and to use just the first part as to train the neural network, okay, to do gradient descent and to do backpropagation. These will not actually be used. These will just for each epoch the model will be updated, so we will have the parameter that will be updated with the gradient, okay, and at each epoch the parameter that we have obtained so far will be used to form a model, a temporary model, and the loss on this temporary model will be computed on this other part, validation part. Okay, so this validation part is not actually seen by the neural network during training. It is actually there to output the loss on the validation set. And here we are specifying that the validation set should be 20% of the entire training set. So let's continue. What I'm pointing at here is an important fact, and So if we look at our training set, we would see that actually it is ordered. All the samples with 25 megabit per second of available bandwidth are at the beginning, and then all the rest at the last part. And so if we split our training set in 2 consecutive parts, we will just train the neural network on just the small values of bandwidth available. This is not good. So before training the neural network, it's better to shuffle the training sets by using this function. Now our values are shuffled, okay, and so we can safely train the neural network. Again, as I did for building the neural network, for training the neural network, I'm creating a function, okay. Actually, the core of this function is this, okay, where the model is actually trained on this training set, and I'm specifying here for how many epochs I want to train the model, and that 20% of the training set should be considered as a validation set. I'm also adding other functions, other optional functions here. You see these callbacks. So callbacks are operations that are done during training. And so at each epoch, in addition to perform gradient descent and backpropagation, we also tell our model to perform these additional things. Let's see what are the callbacks I added here. First is the plot callback. This is just to plot the training and validation loss during the training process. So for each epoch, I will see the 2 values of training and validation loss, so that I don't have to wait until the end of training to understand what's going on. I can see it directly online. Then I also add a checkpoint callback. This is very important because this is telling that at every epoch or every few epochs, the weights, the parameters that we had so far have to be stored in a file, this NN file that I give as input to the function. This is useful because if your machine crashes or whatever, you have always the last parameters that you've computed in the last training. So instead of starting from scratch, you can start from those parameters when you want to continue your training. And also I added a callback logger that is just to store in a file some the so-called history, that is all the information during training. Actually, the history looks something like this. For each epoch, I store the accuracy, the loss, and also the of the training set, and also the accuracy and the loss of the validation set. This is the history. And so when I call this function that I've just created, I'm giving as input a file. In this case, it is a file in my Google Drive. And in fact, if I go to my Google Drive, I see these files that have been created before, and the training set and the number of epochs. Okay, here we see how the loss evolves epoch after epoch. Here I just run 20 epochs, so there are just a few. And here, look at this. I'm calling again this function train model, and I'm giving the same file name. Okay, so if I do so, this function is going to retrieve the file that is actually the model that I've just trained before, and instead of starting from scratch, it will continue training from the network that I've trained before. So it is actually retrieving this file here and continuing training from there. If the file does not exist, of course, it will create a model from scratch. Okay. And in fact, if you notice, first I was plotting the first 20 epochs, then I trained other 30 epochs. Okay, and if then I plot the entire history that I have in my file, the total of epochs is 50, because 30 are the epochs in the previous run, and the actually 20, and the other 30 are the epochs in the other run I did. Here I was just continuing training my neural network with other 5,000 epochs, and look at what is happening. So, as expected, the training loss continued to go down, but the validation loss at a certain point, after 1,200 epochs more or less, it started to go up. So it means that after this epoch here, I'm going to overfitting my data, which is not good. So after you finish your training, thanks to the callbacks that we established, the model is already stored in a file, an NN file. So we can just load the model and use it for prediction on the test set. So when you use this function, you will have as output the probability vector at the exit of the softmax. So that y hat that we saw in the slides. If you want to know the actual label, you have to use this function predict classes. And this is what we have: the class number 1, 1, 0, etc. Class number 2, 4. And as we did for logistic regression, we can then compare the true classes with the predicted classes to measure the accuracy, and more importantly, to plot the confusion matrix. Here is the confusion matrix of given by our neural network on the test set. Observe that we are good at predicting available bandwidth of 25 megabit per second, but we are less good for 50 megabit per second. Also see that there are not the numbers here. It means that actually our model predicted sometimes the bandwidth of 37.5, but actually this value didn't exist in our test set. So of course, this is what I showed is just an example. First, because the experiments are very limited. Okay, we have just links with capacity 100 and also cross traffic of 25 or 75, etc. So we are not sure if the same model would work in real life, but as an example, I think it was interesting to show. Then you can improve this model by use another callbacks that I didn't use in this notebook, called early stopping, that I explained in the slides, which allows to stop training when you see that your validation loss is starting to increase, and so it means that you're starting to overfit. So now we have shown neural networks for a classification problem, but for a regression problem there is no difference at all. It's just that the final layer will not use softmax, but will just be a simple layer with no activation function. So I put here the reference to the code to run a regression model, but it's actually the same. That's all for this lesson. Today we have seen neural networks. We have seen that they are composed by a single elementary unit called neuron, which is described by a set of parameters called weights. And so the entire neural network is described by the parameters of each single neuron. To train the neural network, we have to find the best parameters, which allow to minimize the loss function. In order to do so, we solve the usual optimization problem, which consists in minimizing the loss function, and we use gradient descent to continuously update the parameter vector up to a point in which we reach a minimum of the loss function. In order to apply gradient descent, we need to calculate the gradient of the loss function. To do so, we use the propagation algorithm. Then we also discussed the various hyperparameters determining the good functioning of a neural network. And we also understood how to program a neural network in Keras and TensorFlow. In next lesson, we will see random forests that are learning methods based on a completely different idea, and you will see that they are also very efficient and relatively simple.